So for chapter 5, my note packet starts right away with this temperature equation relating heat with changes in temperature. The textbook chapter goes more into some background talking about what the difference is between heat and temperature and specific heat. So I definitely recommend you take a look at that. I'll point out one difference here between temperature and heat. Temperature is an intensive property, so if you have a large sample or a small sample, it could have the same temperature. It's a measure of the average kinetic energy of the particles inside your material. So if you have a high temperature material, if it's hot, the particles are all vibrating and moving very rapidly. And if you have a low temperature, the particles are moving slowly. And we've already learned of some units that can measure temperature. We can have kelvins, we can have degrees Celsius, we can have degrees Fahrenheit. Heat is an extensive property, so if you have a larger sample, it will be able to transfer more thermal energy. So if you have a large pot of boiling water, that's more dangerous than a small droplet of boiling water if it touches you. And that is a measure of the amount of thermal energy that a substance is transferring or can transfer. And energy, it talks about in the textbook, is the ability to do work. So it's a little bit different from temperature. And heat is measured, some of the units we'll be using anyway are joules, calories. There are other units for energy as well, and any unit for energy can be used for heat because it is a type of energy. The amount of heat that is required for something is being represented in this equation by Q. So that's the amount of heat or the amount of thermal energy that is required to cause a change in temperature. So temperature and heat are related. When you add heat to something, you can make the temperature go up. When you take heat away, the temperature will go down. So the amount of heat that will cause a change in temperature is equal to the mass times the specific heat times the change in temperature. So the heat is proportional to the mass. If you are going to change the temperature of twice the amount of sample, you're going to need twice the amount of heat. If you want to change the temperature by twice as much, if you want the temperature to go up 4 degrees rather than 2 degrees, and you're doubling the change in temperature, then that's also going to double the heat. This third variable, C, the specific heat capacity, it's sometimes represented with S. So I think some of the lab videos that we have represent specific heat with S, but your textbook uses C, so I'm using that also. The specific heat capacity, I guess the C is for capacity, is the energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius. And we need that because different substances require different amount of heat. So if you had a 10-gram sample and you wanted to go up 10 degrees, it would depend whether that sample was water or copper or ethanol or oil. It depends on the substance. So we need to know the specific heat capacity of the substance you're working with. All right, I thought I was going to get right into the problems, and it looks like I didn't. But let's go ahead and do that now. First, let me just point out that the specific heat capacity, since it's the energy needed per gram per degree Celsius, we have these units, joules per gram per degree Celsius, as one possible unit for specific heat capacity, or we have calories per gram per degree Celsius. And the units for heat we talked about are going to be just the joules or just the calories. The specific heat has these 3 units. So let's go ahead and try this first problem. To figure out the heat that's being transferred, we need the mass, the specific heat capacity, and the change in temperature. The delta T is the change in temperature. So if we are raising the temperature from 22.6 degrees Celsius to 38.7 degrees Celsius, we take the final temperature and subtract the initial temperature, and we get a change in temperature of 16.1 degrees Celsius. So the change in temperature is the final temperature minus the initial temperature. That's how we figure that out. So to go up by 16.1 degrees Celsius for this amount of material with this specific heat capacity will require 203 joules of heat or thermal energy. So here we have aluminum. It has a slightly different specific heat capacity. And again, the change is the final temperature minus the initial temperature. This time we are going up by 7.5 degrees Celsius. Be careful because this is one of those rare occasions where we have addition and subtraction in our problems. Lately it seems like we always have multiplication and division, but subtraction goes by the place value, so even though our temperatures had 3 significant digits, our change in temperature only has 2. Alright, so I've copied down our mass, our specific heat capacity, our change in temperature. I didn't point out before, but the specific heat capacity, having 3 units actually helps because now the grams can cancel and the degrees Celsius can cancel, and we're left with a unit of energy, which is good for having heat. The same thing happened before. We were left with joules. And in this case, we have 77 calories as the amount of heat needed. This next problem illustrates the difference between specific heat capacity and heat capacity. So specific heat capacity is the energy per gram per degree Celsius, whereas the heat capacity is for a certain object that you know the mass of. What are the joules per degree Celsius for that object? This heat capacity, represented with a capital C, is going to be dependent on the material it's made out of and the specific heat capacity, and also the mass or the size of the pan. It's going to take more energy to heat up a large pan than it is to heat up a small pan. Alright, so both of these are made out of iron, so we use the specific heat capacity of iron. For the small pan, it's 885 grams, so the grams cancel, and we are left with 397 joules per degree Celsius. So for every degree Celsius in change you want to cause in this small pan, you're going to need 397 joules. For this large pan, I've converted 1.213 kilograms into 1,213 grams, and the grams then cancel. So for every degree Celsius change in this larger pan, it's going to take more energy, 545 joules per degree Celsius. So the difference between specific heat capacity and heat capacity is that specific heat capacity is an intensive property. It has the grams in the denominator. It will be the same for anything made out of iron, whereas the heat capacity is extensive. It depends on the amount of material that you have. It's going to be larger for a larger mass object. And the grams is not in the denominator. It's just joules per degree Celsius. And we're going to be using these heat capacities as our calorimeter constants in the next section when we do some calorimetry. We will find that our calorimeter constants are heat capacities. They have the units of joules per degree Celsius. So here we want to just keep specific heat capacity and just change the units from calories per gram degree Celsius to joules per gram degree Celsius. And to do that, we need the relationship that 1 calorie is exactly 4.184 joules. It is defined that way. It used to be defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius, but it has been redefined to exactly match 4.184 joules. So to convert these units, we will use that relationship. We want to get rid of calories and start talking about joules. So we put calories on the bottom so that it will cancel. So with the units joules per gram degree Celsius, the specific heat capacity of gold would be 0.129. Alright, this next problem is a little bit unusual. So the way we originally had our formula written, we were solving for heat, but it's a fairly simple formula. You can solve for the mass, for the specific heat capacity, or for the change in temperature if you just rearrange this equation. And what we are looking for is the final temperature. What temperature will it become? So remember, our change in temperature is our final temperature minus initial temperature. And when we rearrange that, we get that our change in temperature plus our initial temperature will be our final temperature. And that makes sense. If we have a 5-degree change in temperature and our original temperature was 35 degrees, we would end up with 40 degrees. So that means we need to know what this delta T is so that we can add it to the initial temperature. So if we solve this equation for delta T, we get Q over M times C. So let's plug in those numbers. So our heat is 487 joules, our mass is 235 grams, and our specific heat is 2.376 joules per gram degrees Celsius. So instead of having a slash in the denominator over here, I'm going to use the slash that is already here. When you divide by joules per gram degrees Celsius, the gram and degrees Celsius are going to be on the opposite side of this slash over here. So if something's in the denominator of the denominator, it's actually in the numerator. And it's helpful to write it this way because then it makes it easier to cancel the units. You can see that grams will cancel and that joules will cancel and that you're going to end up with degrees Celsius, which makes sense for a temperature change. And this ends up being a fairly small temperature change. It's only 0.872 degrees Celsius. So let's go ahead and add that to our original temperature. So when we add 0.872 degrees Celsius to our original 12.7 degrees Celsius, our calculator tells us 13.572 degrees Celsius. But of course, it doesn't make sense that we would know this temperature so precisely when we didn't know the original temperature that precisely. We only knew it to 1 past the decimal. So this has uncertainty both 1 past the decimal and 3 past the decimal. So we should round this to 13.6 degrees Celsius as our final temperature. All right, this next problem, we are trying to calculate the specific heat capacity. So this time we know the heat and the mass and the change in temperature. We're trying to calculate C. And so that would be Q over M delta T. Our delta T, we start at 99.3 and go down to 26.4 degrees Celsius. So that is a negative 72.9 degrees Celsius temperature change. Our heat change is a loss of 234 calories. So we are losing 234 calories, which is why we end up with a negative temperature change. And the mass is 34.85 grams. And our result for this is a specific heat capacity of 0.0921 calories per gram degrees Celsius. So then there's a table in the textbook that has some specific heat capacities of common metals. So we could try to see if we can identify which metal it is. The only thing is that table has the units in joules per gram degree Celsius. So let's go ahead and convert this to joules per gram degree Celsius to make it easier to use that table. So we'll use the relationship that 1 calorie is 4.184 joules. And we get a specific heat capacity of 0.385 joules per gram degree Celsius. So here's table 5.1 in your textbook. And just to point out that these units are in joules per gram degree Celsius, they put it in the heading rather than putting it next to each value. So that is why I converted it to joules per gram degree Celsius. But there is one that is 0.385 joules per gram degree Celsius, and that is copper. So this next problem over here is actually in section 2 of the chapter. So I get right into it in the note packet, going straight into some calorimetry problems. That is where we use water since we know the specific heat capacity of water, we can figure out how much heat is going into or out of a system by putting some water next to it and measuring the change in temperature in water. So that's what these calorimetry problems are doing. But I'll go ahead and put that in a separate lecture because there are quite a few of them.